Hello and welcome to this new edition of the Foojay Podcast. We'll talk about TornadoVM, which allows you to run Java code on CPUs, GPUs, and FPGAs.
Welcome to the Foojay Podcast, all your news about OpenJDK.
Today, we're talking about the TornadoVM project. It's a programming and execution framework for offloading and running JVM applications on multi-core CPUs, GPUs, and FPGAs. With the same code, some of your existing programs can be executed hundreds of times faster. Now we're going to go and introduce the guests.
Hello. My name is Juan Fumero. I'm a research fellow at the University of Manchester, working on compilers, parallel programming models, and runtime system for heterogeneous hardware. So I joined the University of Manchester back in 2017, late 2017, right after I finished my PhD, and I joined directly in the TornadoVM team. Since then, I have been working on TornadoVM as now I'm one of the main committers of the project, and I also doing some work in the software architecture in combination with Thanos and Christos. I have experience, more than 10 years experience working around GPU compute for diverse compilers, C, C++ based compilers with OpenACC, and then I jumped to Java back in 2013. I did my PhD in the Java side, and I did something similar with TornadoVM. It's kind of the father of Tornado, in some way, the precursor of TornadoVM. In my PhD, I focused not only on Java, but also other JVM-based languages for R and Ruby to run on GPUs as well. And since then, I have been sticking with the Java side.
Hello, my name is Christos Kotselidis, and I'm an associate professor at the University of Manchester and also chief engineer at KTM. I have been doing research on Java and Java Virtual Machine for more than 15 years, mainly on compilers and memory optimizations at the various levels of the JVM. And I'm leading the TornadoVM project from the beginning, which is almost 8-9 years now. Throughout the years, we have been developing and improving TornadoVM and trying to help developers get the maximum performance they can get out of the Java Virtual Machine. In my past life, I have been working at Oracle and Intel on the hardware and compilers, and I will continue that work now at the University of Manchester.
Hello, I'm Thanos Stratikopoulos. I'm a research associate at the University of Manchester, and I have joined the TornadoVM team 4 years ago. My expertise is mostly on the field programmable gate arrays, FPGAs. So in my PhD, I used FPGAs for accelerating storage. My experience in Java and compilers is also coming from the time that I started the TornadoVM work. And I have done some work also with instances in the cloud for hardware acceleration of different Java applications.
Yeah, my name is Jakob Jenkov. I'm a Java developer since 1999 and a Java champion. And I've been interested in performance optimization since I was doing assembly language programming on the Amiga 500. So it's been a few years. A couple of years ago, TornadoVM popped up on my radar and I found it very interesting. And then I think sometime this year, or was it actually, it was late last year, it popped up again. And some of the things that I was missing the first time I saw it was now implemented. So I thought it was about time to have a look at TornadoVM again. So that's why I'm here mostly as a guest and as an interested user. So yeah, I have just been able to run one of your tests today with TornadoVM, and I got I think 1100x speed up on one of the cases here. So that was pretty impressive.
And I'm Erik Costlow. I'm on the Azul product management team, and I focus on the intersection of Java and security, of how do we make our applications run fast and how do we defend them against modern threats. All right, now we've had a couple Foojay articles about TornadoVM. One in particular talks about the role of hardware acceleration for TornadoVM. And Jakob, how you got what you introduced as about 1100%? That's pretty significant. Who wants to go through and just summarize what we talk about in the Foojay article about how TornadoVM works and when and where you use it?
Sure, absolutely. So let me summarize TornadoVM. In a nutshell, it is an open source software plugin to different JVM distributions that unlocks hardware acceleration on multi-core CPUs, as you said, GPUs, and FPGAs. The main objective of TornadoVM, it is that hardware acceleration was not by design included in the JVM. Therefore, we wanted to add it in a programmer-friendly way. And we have many different features exposed in TornadoVM. So we support portability across different hardware vendors, portability across different hardware device types like multi-core CPUs, GPUs, and FPGAs, and also through the interoperability with GraalVM, we can accelerate, we can invoke from different programming languages that are implemented on top of Truffle, the Java accelerated code.
So how exactly does that work? We have a normal Java application that we run, probably something that's got to be a little more advanced than Hello World. But let's say I just took something like Apache Cassandra and I drop it into TornadoVM. Does it automatically offload onto GPUs, or do programs need to be rewritten to indicate which portion goes onto the GPU?
In general, the way that TornadoVM will be integrated either in some user code or in another platform like a Cassandra or Apache Flink that we have done already the integration, it differs. Essentially, acceleration on GPUs or FPGAs is not always successful, meaning that these kind of devices, they are very good at particular types of workloads. So there is some help needed by the developers in order to identify which parts of their application can actually benefit from hardware acceleration. Therefore, we have this type of different devices because each one of them is really good at a specific task. Now, if somebody starts from scratch an application or they have their own application with their own libraries, the idea it is to use the APIs provided by TornadoVM in order to offload their preferred tasks on the accelerators. If we want to integrate a larger framework like Cassandra or Apache Flink or Apache Spark with TornadoVM, then the storage becomes a little bit more complicated because this integration normally happens at the systemic level. The idea for TornadoVM is that developers shouldn't care too much about what's happening underneath. The same way that the JVM or the Java programming language was created with we write once and we run everywhere, in the same spirit, we also try to carry it through this kind of, let's say, new accelerators. So a developer of Cassandra, for example, which is used to using the APIs of Cassandra, ideally should get this acceleration out of the box without even noticing that TornadoVM it's working underneath. So for this kind of large-scale systems, normally what we do, we go inside and we do the integration under the hood. So developers will keep using their APIs as they used to. Now, for applications that or frameworks that we have never seen before, this is user code, then a developer can actually use our APIs to create their applications from scratch.
All right. Now, I don't know very much about GPUs. Most of what I know how to do is to play a game, which means that I have the right driver installed, and I just open something up like Minecraft, where you can do redstone programming because it's written in Java and is a great game. So when you talk about Java developers being able to drop their program onto a GPU and TornadoVM kind of figures it out, first, what's the limit that your average developer should know about knowing what loads on certain GPUs so that we can just get a feel for it? And then what's some of the more detailed information that they probably shouldn't have to know?
Yeah, so that's a great question. So we try to hide in the Tornado side as much as possible, as much as complexity as possible from the GPU programming side. So you mentioned that for video games, for example, you just need a driver. For programming more than video games, you also need an actual implementation like CUDA or OpenCL. And Tornado actually makes use of those implementations. In fact, there are actually already 3 backends. So from the programming side, we tackle we have been thinking about programmability for quite a long time already, and we think to just use Tornado as simple as possible, in the sense that we used to program, sequential programs. And we want to do is to add minimal information to the sequential program in order to be able for that Tornado compiler or any other compiler to parallelize the application, to transform that sequential code into parallel code. For example, from Java sequential code to OpenCL or CUDA code. And then Tornado will handle this transformation, those optimizations, data manipulation, buffer creation, kernel execution, etc. for you.
In the case of Minecraft, for example, if you have this code base in Minecraft and let's say you want to do some ray tracing, for example, let's say, and I'm aware now that Minecraft supports add-ons to have ray tracers in OpenGL. So in a scenario where somebody would integrate TornadoVM with Minecraft, then we shouldn't have to write these OpenGL functions. The Minecraft code base should still stay in Java and use TornadoVM to program those functionality. We have projects within our team where we actually have implemented a ray tracer in Java, a single-threaded ray tracer in Java, accelerated with TornadoVM, where we can get real-time over 60 FPS of performance. So if Minecraft wants to do the investment and keep the whole stack in Java, the Java ecosystem with all the benefits that this can bring, then anybody that would write, let's say, some GPU kernels in OpenGL or OpenCL or CUDA and plug them to Minecraft, now they can write them in Java, which is easier, and TornadoVM will do the heavy lifting of accelerating those on the GPU.
All right. So one of the things that I do know about GPUs is they do a lot of really multi-threaded applications. So whereas a CPU might have, 8 cores, 32 cores, or some number, the GPUs seem to have like thousands of them. So what are the real differences between a thread, as I would think about it from a CPU programming, and a thread as I would perceive however a GPU parallelizes it?
From the GPU perspective, when we call thread, it is like a lightweight thread on the GPU. We prefer to call it instruction streams because actually they are correctly executed in a stream fashion, like in lockstep. It's a bit unusual if you're coming from the CPU side, how these are programmed. I can give you an example. So let's say we want to operate with 2 arrays. We want to sum up 2 arrays, okay? A plus B. So the way to do it on the CPU, let's say we use C or we use Java, multi-threaded, we split, let's say we have, 8 cores or 32 cores. We give each core a portion of the work to do. And that could work, right? That can work. On the GPU side, we prefer to do in another way. So we specify the work to be done per thread. And then we just, when we launch those kernels, we just call multiple instances of that kernel. And we map the input space, in the iteration space of the input size with the number of threads to be deployed. For example, if we're running an application that has input size of 1 million elements, we will launch 1 million threads. Obviously, we might not have the resources to run all of them in parallel, but the GPU driver and the GPU hardware will take care of splitting these 1 million in smaller blocks in order to run as efficient as possible.
Okay, so Jakob, what are some of the workloads that you put onto TornadoVM? Like as somebody who uses it rather than works on it, you have your choice of when do I reach for a regular JVM and when do I reach for TornadoVM? And how do you really go about making that decision?
To be honest, at the moment, I haven't gotten any further than trying out some of the samples that come with the TornadoVM. But the kinds of workloads that I would be looking for are definitely data-oriented types of workloads where you have to scan through large arrays of data, typically stored in memory or stored sequentially on disk. So you load them in really quickly, you pass them on to the GPU, and the GPU can do its calculations really quickly. So those are the kinds of workloads that I'm looking to run with TornadoVM. I'm not sure if you mentioned, but like one of the things that I found interesting as well is that it's not just the GPU that it can run on, but like you also just parallelize on whatever idle, or not idle necessarily, like CPU cores, right? So one of the other things that I'm hoping one day will be possible with TornadoVM is a lot of desktop computers today come with at least 2 graphics cards, right? One built in and then an extra one. And I'm hoping one day it's possible to use TornadoVM for like desktop type applications. But at the moment, I think the installation process is maybe needs a little bit streamlining or whatever for that to be possible. But this is one of the things that I think would be really cool to couple it with JavaFX, and then we could see some really high-powered Java desktop applications.
In terms of those desktop applications, a lot of people have Mac. You've got either the M1 or M2. And Thanos, you wrote a recent article on Foojay just talking about some of the test benchmarks of TornadoVM. And I think you saw something on your M1 MacBook, like a 738 times performance increase, or something just really, really high. So can you talk a little bit about that and what you see?
This was an implementation of the matrix multiplication. In fact, it was an implementation using the TornadoVM APIs. By that time, I was using also the x86 binary of the JVM build on my M1 ARM that was going through the binary translation to run on the system. I was impressed because it was the first time that I tried TornadoVM on the M1, and it was quite straightforward. The things that we had to adjust in TornadoVM was just some things in the drivers. Because we have seen also that Apple is deprecating the support of OpenCL, I was a bit skeptical when I was trying that, but finally it was supported, and I saw that all our unit tests that they were running on my previous MacBook, they were running also on the M1. It was very interesting to see that with TornadoVM, we can unlock this high performance, as you said, with the speed up that I got, compared to a single-threaded Java application that was running on the MacBook. But it's also more interesting to find other things, like, for example, the energy efficiency of these implementations, because we're talking about the ARM. But this is something that is ongoing on our team to enhance TornadoVM with this energy efficiency functionality.
All right. Now, a lot of the data intensive workloads that we have, like we talked about TornadoVM being really good for computation based. And when we have to go with huge amounts of memory and huge amounts of data, the majority of us are going to the cloud with like AWS or Azure or GCP, where you just buy like an EC2 instance. So what are you doing for TornadoVM instances up in the cloud? Like, are you buying the same workload types, or how are you handling that?
The workload types and the trying to find the applications or the use cases for TornadoVM, it's actually one of the hardest parts that we are working at the moment. Because Java is so ubiquitous and it has been used throughout the years for many different domains, from server development to desktop development. It's always, I wouldn't say tricky, but it's always very unique in the way that the developers try to approach different kind of problems by using the same programming language. So the expectations, or at least the workloads that they want to run, and everything that comes with it, for example, data sizes, computational density, and where Tornado can fit inside and help the developers. It's actually one of the challenges we have as technology developers in order to find this sweet spot. Which is the sweet spot for a specific, let's say, a group of developers that they develop either with JavaFX, or they run through another framework on the cloud for some heavy-duty computation, in order to accommodate all, let's say. This is our wishful thinking. For us, it doesn't matter if it's like a MacBook Pro or a cloud instance. Our objective is one. If you have a GPU or an FPGA that can unlock your 10x, 100x, we want to give it to the developer. Now, the question is how it's easier for the developer to actually use our system in order to achieve those speed ups. This is an ongoing process, and we engage also with developers to try to learn more what are the workloads and how they use them in their framework in order to do some changes in the API, or even add some features that are really important for the specific workload. So TornadoVM now, it can be used on any laptop, download it, or even we have Docker images, and also have tested on Amazon Cloud that have GPUs and FPGAs. So we know that TornadoVM can run on these platforms. And how developers will utilize TornadoVM inside the ecosystem in this complex application. This is a discovery phase for us. And it differs a little bit from traditional C or C++ developers in a way that when CUDA or OpenCL came, they were very similar in how to use them, like a C++ code, or even it was very natural for developers of C to call a CUDA kernel. In the Java world, it's a bit different because Java virtual machine has the garbage collector, the memory management, and developers normally don't worry about those kind of things. So if you want to harness a GPU, we don't want developers to reason about where this buffer will go, how the garbage collector will treat it, is it going to segfault, I'm going to have diagonal pointers, or how to have consistency, how my for loops should be constructed. And this is something that we have been iterating a lot. For example, in our latest version of TornadoVM, we have refactored significantly the API because we found out that the original API was a little bit confusing for developers in order to distinguish the notions of computation and data management, data movement between the different accelerators. So this is a work in progress for us also to find out these answers.
Got it. So we're talking about the API that developers interact with to run better on TornadoVM, or maybe I recognize that I have that data-intensive processing. What is the API and what should I know about how to structure my application? Like, is it annotation-based? Is it inheritance-based? Like, if I want to write something to run really well on Tornado, what code paths or API do I interact with and what should I know?
As Christos mentioned, we refactor quite a bit the APIs in the latest release. And we have been thinking quite a lot about this for a long time. So one of the questions we ask in order to have a parallel application, not just for Tornado, but in general, is first of all, how do we represent parallelism? So in the case of Java and in the case of Tornado, we have two options. One of them is through annotations. So we instrument or we instruct code somehow with annotations to give the compiler some hints about how to parallelize things, how to parallelize loops. That is the most expensive part. So one way in Tornado is through annotations, and the other way is through what we call a kernel API. The difference is that the annotations, as we mentioned at the beginning, is that we annotate code, that Java code that is sequential. We annotate sequential code. This is similar to, for example, OpenMP or OpenACC models for C, C++, and Fortran. And this is nice because we don't have to reason about how to parallelize things that much. We can express our computation in a sequential manner, and the compiler will do the magic. Somehow will do the best to map it. But this sometimes could be quite limited. So we opened recently another way to express parallelization, what we call the kernel API. And this kernel API is very similar. Actually, we borrow terms from lower level models like OpenCL and CUDA, and you express kernels in a very similar way. So instead of annotation of loops, we express the work to be done per single thread. And then what we do is to launch hundreds or millions of threads on the GPU. This is the problem of how to identify parallelization. Then we have a second problem that, okay, we annotate loops, for example, at the method level, or we express kernels with the kernel API, but we do this only at the method level. So we compile at the method level, and that's where we'll constitute our kernel. And the second part is, okay, along all these methods that I have from Java, okay, from different classes could be, which ones I want to offload. Okay, so the first problem was about how to identify parallelization and how to provide parallel kernels. And this problem now is how I select different kernels to be offloaded. And we do this through what we call a task graph. So basically, it's a data structure that Tornado provides. It's very easy to use. And you can build graph and you attach data and code. Yeah.
So as the engineer who's writing my application, I should know the task graph because that's how I structure out my work to be done.
Exactly. So basically, a task graph is just how data flow is flowing across different methods that you want to call and offload.
Can I just return for a short moment to using TornadoVM in the cloud? Because my day job is as an AWS solution architect. I would like to try running TornadoVM in an AWS Lambda in a serverless execution environment. And I know that AWS Lambda can run Docker containers. And as far as I remember, there's a Docker container with TornadoVM packaged inside of it. And I also know or remember that with AWS Lambdas, when you make them a little bit bigger, you also get some virtual CPUs. And if you want to use those virtual CPUs for parallelizing work, you will have to do it like manually in threads, but it would be nicer just to be able to let TornadoVM utilize those extra virtual CPUs. It's getting especially interesting since I think the last AWS reInvent, where Amazon launched this snap start. So now the Lambdas, Java Lambdas, will have a very low cold start. So Java is really becoming a first-class citizen in the Lambda world now.
Since I'm a part of Azul, I got to talk about Crack, which is the core that SnapStart is based on. I got to share the enjoyment for the OpenJDK Crack project. Do you really, like when you run on Lambdas, do you get to use much GPU? Like I have no idea what CPU instance or anything that Lambdas even run on.
There are no GPUs or FPGAs available through Lambda, but you get the extra virtual CPUs. And I was wondering if it was possible to have TornadoVM utilize them someday.
I have no experience on Amazon Lambda, to be honest, so be cautious with my comment now. But if those instances support OpenCL or any other compatible model, we should be able to run, right? For example, yesterday we did a quick test for one of our projects. We plug in an open source implementation for OpenCL running with pthreads on the CPU in a Docker image. So that was fun. We could do this. So I have no idea about Amazon instances, but yeah, something we can try.
CPUs are a little bit under-discussed in the context of TornadoVM. Normally people think TornadoVM and they automatically think GPUs or FPGAs. But the matter of fact is that since we compile Java bytecodes to an underlying representation for parallelism like OpenCL or PTX for CUDA or SPIR-V, essentially any CPU that supports those drivers, like OpenCL drivers for CPU, through TornadoVM, they can also get the parallelization, right? So if you have a loop and you annotate it and you run through Tornado, then Tornado will parallelize for the 8 CPU cores that you might have. And on top of that, those drivers, they also apply automatic auto-vectorization. So even if you don't have a GPU and you have a parallel for loop, or I don't know if it's on a cloud or a desktop, and you have a parallelism and you run through Tornado, the performance that we get normally, it is even higher than Java threading, because we stack up both the parallelization plus the auto-vectorization that some of these drivers can give you. Your starting point, again, it is a serial for loop with an annotation. So going back to Jakob's question, if you have a Lambda, again, we have never played with Lambdas, but if you have a Lambda on an Amazon instance with some visual CPUs, and there is, for example, an OpenCL driver installed on that instance, Tornado should work out of the box, for example.
Cool. So I got the AWS ECS guide up here that talks about a bunch of instance types where you've got, your P3, your G3. Looking at each of these, which of these AWS instance types do you look at and just think, wow, I want to run on that? It would be really hard to max this whole thing out. Like I see a P2 16X large has 16 GPUs with 192 gigs of memory. And a P4D 24X large has 8 GPUs and 320 gigs of GPU memory. Like, which of these just feels the coolest for you?
The largest, for sure.
I think
I would say the maximum, yeah.
we always trying to get big numbers. That's a fact. So as soon as we start teraflop territory, we're always very happy. But in general, it's a trade-off. So you may have a very huge GPU, but you may never be able to utilize it because all depends on your workload and your data set. And we have done research that proves that in some cases it's obvious you go for the highest GPU, highest memory, because this is what you need. But sometimes the winner, and I'm quoting the word winner because this depends on the SLAs of the application, they're a little bit in a gray area. So you have the same kernel, you adjust a little bit up and down your data volume, and then the CPU can outperform the GPU because you always have data transfers between the devices that you have to account. So, but general rule of thumb, if you have acceleration, the bigger the better for us.
We somehow overpass integrated GPUs. Same with the CPU. Also, many CPU systems, for example, my laptop has this Intel CPU and has an Intel integrated GPU. It's not that big, that fancy compared to the NVIDIA one, but it's usable. And Tornado can use it in a transparent manner. The thing is, there are some type of applications, because we share memory, that because we don't have to perform these data transfers back and forth, it's worth executing on that GPU. Can give you a higher performance than a discrete GPU.
Talking about those GPUs, you mentioned a couple of the languages, and I know a lot of software engineers, you can kind of flip between different languages. Like, yes, people can write Java. Sometimes maybe they'll flip over to a Node, then maybe they'll jump over to Python. But in the GPU space, you've got like OpenCL, you've got CUDA, and just what's the difficulty associated with writing a direct OpenCL or CUDA program? Like, since you guys know how to write them, how hard is that? Is that like something that normal people do, or is that something where it's like, ooh, I shouldn't invest time in kind of learning that unless I really am interested?
I myself, I am very fan of CUDA. So that's the first language, GPU language I learned. Then I swapped to OpenCL.
I like that you differentiate GPU language from regular language.
GPU supports a subset of what we call a language, right? Doesn't support a whole C program or C++ program. Programming for GPUs is an optimization problem. And as any other optimization problem, you need to know architecture details. And GPUs are different from CPUs. So I can give you a very easy example, reductions. So let's imagine that we have an array, a plain array, and we want to perform a reduction, sum all the values. So from an array, my input, the output is a scalar value. Now, I want to run this reduction on C, right? Or just Java. I just write a for loop and just sum the elements. But now, so the GPU or any other highly parallel programming language, now reductions depend on values computed from the previous iteration. So to perform a full reduction, I should restructure my algorithms quite a bit. And to put things even worse, so data is not shared with all elements in the GPU. So we need to be careful. So we need to split data in smaller chunks, and it's only shared in smaller chunks. And we need to know which processors contains that data. To put things even worse, cache is not coherent. So if we want access to the right value, we need to put a variable to synchronize all elements. This is just for a simple reduction, right? It's fun to do it. You can do many, type of reductions and so on. But Tornado or frameworks like Tornado can do everything automatic for you.
Got it. So I feel like people can kind of pick Java up, and you can go from like 0 to like, yeah, I'm familiar with that. I did it in a weekend, a week, or some kind of short time. It feels like I'm not going to become super proficient at like CUDA programming on a Saturday.
It depends of the background. So if you are used to GPU programming for a while, those terms sound familiar already for you, right? So having a CUDA kernel and then going to OpenCL or one API, the latest from Intel, is similar, right? If you're starting fresh, you need to catch up with a lot of new terminology, not just the programming side, but also the architecture side. And that could be one of the obstacles to face GPU programming in general.
And if you target FPGAs, then it becomes more complex also. Because FPGAs are way different.
Yeah, I don't even want to approach that as a regular person.
And even just if we return to these potential use case for desktop applications, as far as I can see, in the next generation of Intel CPUs, we get a lot more efficiency cores for free, even in the small CPU lines. So it would be really nice to be able to just utilize them as well, semi-transparently with TornadoVM. And like my impression of the API so far is that it seems reasonably easy to approach. Like you say, Erik, it's probably something you can get the hang of in a weekend or so. The API and the annotations for TornadoVM.
For the Java side, I feel like I could write a
exactly.
TornadoVM application in a weekend, but I feel like if I had to learn all the intricacies of a GPU to program directly on CUDA or OpenCL, like, boy, I better clear my calendar for that.
Well, to be fair, just to clarify, so those models, CUDA and OpenCL, usually offer libraries. So many people approach first by using libraries. CUDA has these many libraries for deep learning, machine learning, etc. One of them for array compute is called Trust, CUDA Trust. And that's the way to go, but similar to Intel One API or OpenCL. So the way should be through libraries. Then as soon as you require more expertise or do more fancy things, you can tune low-level kernels directly.
Yeah, I kind of like the approach that TornadoVM is taking, though, because I can write the Java code and I can have the Java code work well. You know, we got the write once, run everywhere thing. So you got write once, now run on GPUs. I feel like if you go straight to CUDA, you've got like write once and then you switch your CPU and you have write again.
Exactly. And also the deployment is a problem because you have to bundle these libraries inside your Java code and ship them. And as you said, as soon as you change the hardware, okay, CUDA per se has a vendor lock-in. So if you go CUDA, then you are locked in NVIDIA. Let's say you go on OpenCL to have more, let's say, variety of devices.
Looking back, using what you're talking about with the difference between like an AMD and an Intel, when I looked at that AWS sheet there where they say, here's what you can buy, they told me the number of GPUs. They don't say, is it an Intel GPU? Is it an AMD GPU? So I could probably figure that out, but I feel like if I code and I choose the wrong one or I choose the right one and then it gets changed, that seems problematic if I'm having to go direct.
Definitely. And I think if we see the industry now, both AMD with Xilinx acquisition, they're trying to create their own unified programming models, and Intel also with their own lineups, they try to create their own programming models. And what all of them have in common is that they're trying to create the singularity, this single API, which is very good for developers, and then the vendors will optimize underneath. So there are many initiatives from Kronos Group or One API that they're trying to bring, even in the non-Java world, all these companies together to help developers to harness this kind of accelerators easily. So it shouldn't matter if it's going to be an AMD GPU or an Intel GPU or an NVIDIA GPU. The same way, for example, now, at least for us, for the Java people, the JVM guarantees that if you run on an Intel GPU, you're going to get very good performance if you run on an AMD CPU. And the reason for that, because Intel and AMD or ARM, they do the intrinsics at the compiler level and they optimize the platform for this kind of architecture. And I think this is a good thing to have as a community, this safety that the JVM is optimized for all platforms available.
Yeah, just to complement what Christos mentioned is really a good point. Even if we go to the root of a pure OpenCL, OpenCL is a standard. It's maintained by Kronos Group. It's a consortium of many companies and institutions, and they agree on the APIs, and each vendor can implement the API. So what you can have is your OpenCL program running on Intel and tomorrow running on AMD or any other vendor from different companies, and the code will run. So they guarantee functionality portability, let's say, but performance portability is another thing, right? That means that maybe you have performance for one platform, but achieving performance for another platform is very difficult. Tools with Tornado, we have a lot of work. We have spent a lot of time, a lot of work tuning the JIT compiler to try to, work on the performance portability side, especially on the FPGAs.
Yes, and I have tried, as a person that I have tried the TornadoVM on the AWS instances. I have installed TornadoVM, the software, both on instances that they have AMD and NVIDIA GPUs. And I have seen that you need also to install the drivers, although there is guidelines from AWS regarding finding the correct drivers to install. But regarding the installation of TornadoVM, it is similar and smooth, especially on Linux systems with the automatic installer script that we have online. Also, the same stands also for the FPGA instances that we have tried, which is the F1 instances. But coming back also to the previous question, we haven't tried on the instances that they have multiple GPUs. And the reason is that we couldn't afford one. They couldn't give us the access to this kind of instances.
Yeah, that's the downside of being a university.
Exactly.
Got it. The university doesn't just spin up cloud resources and then leave them alone like a lot of companies do and forget about them.
We have some credits, which is good for research, but the credits were not enough for the research part to give us, the access to the huge instances that they have, the multiple GPUs, which is something interesting that we are also very interested in. We have done some work to concurrently access the devices at the same time.
Given the number of GPUs that some of those systems have, you guys could probably team up with a group that needs to heat a building.
True, we do that. In the future that we have in mind, this is the goal. If GPU programming, especially now with AI and machine learning, GPUs are a key player into this kind of workloads. And Java to get a foothold in this ecosystem, because now, for example, PyTorch and these kind of frameworks are more widely used. And GPU becomes part of the equation for the Java virtual machine. This is our objective, how to help developers in Java do their stuff. And in that moment, with so many billions of Java developers, we're going to be able to hit a lot of buildings with TornadoVM.
Yeah, I've actually seen the ChatGPT guys talk about, however many GPUs they have, and those guys talk about GPUs a lot. And, now that Java code can run on GPUs, what's going on in that space? Like, why are the ChatGPT guys always talking about GPUs? And, Java has TornadoVM. Like, what does that bring to us?
That's a very good question. And I think now we're going to philosophical discussions about this future. The truth is that I don't know how ChatGPT does it internally, but the majority of the machine learning frameworks and AI frameworks are being used. They're using under the hood optimized libraries for training the models from NVIDIA or from Intel. For example, they use 1DNN or CUDA-DNN and this kind of libraries. And normally, in front of these libraries, which are, let's say, binaries or at least implementations, they have some APIs like PyTorch to actually allow developers to experiment very, very fast. And in the Java world, there are frameworks for deep learning that they follow the same path. For example, there's a Java API that can call a kernel being implemented through a CUDA library to run on a GPU. And this way of programming machine learning models or AI through a Java does not differ at all, I would say, in terms of capabilities from the GPU perspective. Of course, the more APIs we add, the more capable our system becomes. Our vision is that since the GPUs are not, or at least access on GPUs is not yet formalized within the Java virtual machine, and steps are being taken now through Project Panama and this kind of new projects on how to formalize foreign functions, which can actually help immensely this kind of formalization of calling these kernels. We believe that TornadoVM can play a very key role into using our experience and, let's say, our software in order to create such systems that it could be used in a machine learning and AI world within the Java ecosystem. So the same way we have a collection API in Java, to have a machine learning API, that under the hood uses TornadoVM to get out of the box this GPU acceleration.
Yeah, so Panama is one of the OpenJDK projects. Can you just give a rundown of what Panama is and why it matters to the work that you're doing in TornadoVM?
And to be honest, we're not experts in Panama. To our understanding, it has the objective of creating these foreign functions. So I would say like a replacement for JNI, and also to formalize how to do memory allocation off heap. So going back to the problem, or at least one of the challenges that a Java virtual machine has compared to other programming paradigms when it comes to GPU acceleration. In Java, since we have a campus collector, the users are used to creating a new object or a new array, and this array will go into the heap, and the campus collector will take care of it. In C++, no, so you have to manually allocate the data. So the developers know that they are responsible of doing this manually. So when you run on the GPU, in that concept, you're also responsible of creating this memory and copying the data from the CPU side to the GPU side. Let's assume that we do the same in Java, which we do with TornadoVM. What happens if the campus collector hits when the data are on the GPU. The garbage collector will move the data in the host side, on the CPU side. The GPU will never find out because there's no way to find out what's happening on the CPU. And when the execution finishes, it will go back to update the data in the pointer. The pointer will be gone, and then you're going to check fault.
Interesting. So if I can kind of paraphrase that just to make sure I understand it, there's without like a Panama or without the ability to reference memory, there could be a situation where the CPU garbage collector walks around and says, I can clean that up. But later on, the GPU comes by and says, where is that?
Exactly. So what Panama does, it formalizes how to allocate memory outside the heap. Before, Panama, it was unsafe operations. So you were calling the unsafe library to do it manually, and which has some risks. Now with Panama, since you can allocate data off heap, let's say in a formal way through memory segments, now the idea comes, okay, if I know as a Java developer that I can actually do GPU acceleration, then I could directly allocate this data off heap to solve the garbage collection problem, right? Since I know that there's going to be big arrays for acceleration and compute, there is no point of having them into the heap. So I can use Panama, allocate them off heap, and then I'm responsible for that. And as soon as you have Panama as the baseline for that, then you can start building libraries on top of Panama of a whole collection of data structures that can be off heap. And this can really improve performance for specific workloads that they require a lot of GPU acceleration. Hence, you want to get the garbage collector out of the way of making your life more difficult.
Yeah, also with Panama, we can combine the type of buffer with some of the optimized GPU buffer transfer modes. For example, we can do pin memory between the GPU and the CPU, or we can do automatic, a unified memory, use the unified memory, and the driver will take care of migration if needed, back and forth, things like that, or use directly share memory for integrated GPUs. But that's kind of orthogonal to having Panama. So Panama will give us the possibility to exploit all these combinations in a more standardized way.
Yeah, and this is one of the main challenges that, in our opinion, this kind of acceleration, or at least using these hardware accelerators, has been a problem, or at least a very big challenge on the GPUs, because these problems, they require the whole community to come together and think of a solution, like how to design a garbage collector that can tackle data or trace data on the GPU side. Even technically, this is very hard to do now because you need the unified shared memory, which is something fairly new and not, let's say, proven yet. And we are doing, part of us, we're doing research in this direction and provide feedback to the community on how that future would look like.
Let me also complement that when we allocate memory on heap and we jump into the GPU for execution, then the GC is frozen, so it will not perform an actual collection. Otherwise, we would segfault every time that we run currently with TornadoVM.
Yes, to be more technical, we do a critical section on the GenI side just to guarantee that part.
All right, so that's some cool stuff. I know you guys just had a release in February where you rolled out things like the task graph and some annotations. So what are some things that people should do if they want to try out TornadoVM?
The first thing to do is maybe to try the example suite that Tornado has. That's actually the path that some of the potential Tornado users have taken already. So we have a suite of different applications, including applications for fintech or typical things for machine learning and different domains like physics, DFT stuff. And people try, okay, this matches kind of the computation I would like to see, I would like to do. And then from there, they try the examples, they study the code and so on. I will say that's the first thing to do. And then depends on the background of every person, right? So I mean, we have people coming from different backgrounds, and that's the thing. We try to, combine them all. We have had people or developers coming from GPU, pure GPU domain. So that's why we have these kernel APIs. And we have people that are coming from the pure Java side without any GPU background.
Got it. So if I were just a developer taking a peek at TornadoVM, instead of me going and saying, how should I rewrite my program to run really well on TornadoVM, I take a peek at the samples, I run the samples on a CPU, I run the samples on a GPU, I look at the difference, and then I start taking a look and saying, well, what's different about these? And now that I know what's different, once I know it, that's when I start saying, how do I write for TornadoVM?
Yes, and in fact, since the latest release, we have a new documentation site where we document all the programming model of TornadoVM, and we give some introduction of the main features of TornadoVM, how to install it, how to run the examples, as you said, how to try the test cases, the TornadoVM profiler, and other core things.
Yeah, and one last addition to that, the most important is to tell us when it breaks, so to try to improve it. And secondly, as we know that TornadoVM does not support the full Java feature set, because it's not because of TornadoVM, it's because the GPU, for example, has some limitations like performing system calls and stuff like that. So there is a list of things don't supported by TornadoVM. So of course, when we write our application, we have to make sure that we don't use this kind of features.
And are there any major APIs that people should be aware of to say, oh, I shouldn't do this on a GPU? Like it sounds like process builder or runtime.exec.
We haven't narrowed down specifically for APIs, but general reflection. So anything that requires reflection, because you need access to the class pointers, which they don't exist on a GPU, or system calls that they need OS support. These are, in my opinion, the two main features that cannot be executed on the GPU. And there are some other smaller ones, but I think reflection and system calls are the most important.
Okay, and most of the data processing, they don't use that. So I think that's good. Good.
Also, worth mentioning, we have some features that usually, historically are not supported on GPUs, but Tornado can support it. And this is because the JIT compiler, for example, GPUs don't support dynamic memory allocation. But sometimes in Tornado, we can do that because we compile at runtime and we know more information about the actual application. So it kind of, I'm not saying Tornado does support dynamic allocation. I'm saying that because of the compilation nature of Tornado, because at runtime, it can give the illusion to the programmer that some things are supported on top of what OpenCL can give you.
TornadoVM extends the GRAL compiler, and the GRAL compiler is very well known for its very aggressive and very good escape analysis. So although you cannot allocate an object in memory on the GPU, because GRAL is very good at replacing objects with scalars, sometimes the developer believes that there is an object being allocated, but because we use GRAL, this object disappears, and we still can run code that visually looks like it does an object allocation, but in reality, it just has been replaced by scalars. And just to complement the last one, sometimes it might get a little bit intimidating for developers how to transition the code from the pure Java to the GPU Tornado style of Java. Requires some getting used to it. We are working to improve our tools in order to guideline developers towards that. These kind of tools have been existing for, let's say, C++ for many years, like Intel Bitune, where you can actually get even advice on how to optimize it. So we are working to provide something similar for TornadoVM and for everybody that wants to use acceleration through TornadoVM.
So what are your advice to developers who want to take a look at their applications and just figure out where TornadoVM is a good candidate?
We welcome developers to try Tornado, and in order to find out if Tornado can help them, they can just look if they have threading into their application. If there is multi-processing or multi-threading in their application and they're already using Java threads, that's a very good starting point or indication that they can get high performance with TornadoVM.
Try to analyze first the application, if it's memory bound or compute bound. If it's compute bound and you need more compute power to process faster, that's a good candidate. Having enough threads to run. So in rule of thumb, don't go to a GPU just to launch 10 threads. So go to a GPU to launch 100 or 1,000 threads, right? That's another good candidate.
Another factor is also the data sizes, because as we have seen, it doesn't make sense to go to a GPU for an array that has 16 elements, because you will pay the overhead to transfer the data, and this will penalize performance.
All right. Well, thank you very much to all of the guests, and thank you all for listening. And please keep an eye on Foojay for future articles about development and everything related to the Java world.
Give me a Foo, give me a J, give me the friends of OpenJDK.